Hey, so today we will be proving the weak law of large numbers, which says our sample mean converges in probability to our population mean. And where weak comes from is the form of convergence. So this P right here means in probability. If there were a strong law of large numbers or a mean squared law of large numbers, we would kind of just be changing the type of convergence for the sample mean on the population mean. So kind of to even first get to this statement, we have to first understand what sampling statistics are, and then we'll have to kind of prove a couple inequalities, and then we can finally prove the weak law of large numbers. Um, so the first thing we need to discuss is sampling statistics. And so what we have is we have x1 through xn IID random variables, and we have finite mean or finite variance. I mean, I'm sure we also have finite mean, or else I don't think these calculations will work. And if we have these, first, the expectation of our sample mean is the same as our population mean. And second, the variance of our sample mean is the variance of our population mean times the number of samples that we have in our sample size. So this is a theory, this is a theorem. I'm not really going to prove this, but we will have to use these this sample to population conversion later in our proofs. And then the next thing that is a kind of precursor to our Chebyshev inequality is the Markov inequality. So this states if we have a positive random variable x and some constant, some positive constant c, and our expectation of x exists, then the probability that our random variable exceeds the constant is upper bounded by the expectation by that constant. So we don't really know why this can help us, but for now, we're just going to work on proving it and seeing what we can do. So first, given the probability that, or first, we'll start with our expectation and see kind of what introducing C is. So definition of expectation is the integral of x times our PDF, f of x, dx, over the range of values that x can take. So that will be from 0 to infinity. And splitting this up over C, we can say that the integral from 0 to C of x f of x dx plus the integral from C to infinity of x f of x dx. And doing kind of, we know that this is greater than, we know this is greater than 0. This is a PDF, so it'll should integrate to 1. So this entire thing should be greater than 0. So if this is non-negative, then um, this whole this whole thing should be bigger than just this part. So we will isolate this part. Now, we're kind of working on the x range where x is greater than c. So converting our kind of calculus bounds, we want to do set bounds. So this is the same as the integral of x greater than c of x f of x dx. And given that our x values are positive and always greater than c, we can kind of easily note that the same thing is greater than where we had an x, a c, and then f of x dx. And we can kind of take that c out and put back in our calculus bounds, not our set bounds, over c to infinity of f of x dx. And now this part is just a PDF over C, so it kind of is known that a PDF is a PDF over the bounds which aren't the whole reals is a tail probability. So that's the same as our probability that x is uh, greater than or equal to c. And so from this whole thing, we have that e of x is greater than or equal to c times p of x greater than or equal to c. And then therefore, p of x greater than c is less than or equal to the expectation over our constant. And so that is the exact same thing that is stated in the Markov inequality. So we've kind of proved that. And we're kind of only proving this to help us in proving the Chebyshev inequality that we will use to prove the uh, weak law of large numbers. So that was kind of uh, step 2.1. We had step 1, which was our sampling statistics. We've step 2.1, and now we can go to step 2, or 2.2, which is our Chebyshev inequality. And this states that if we have a finite variance, which we almost always have, or almost need, we don't always have it, especially in the case of Cauchy distribution. Speaking of Cauchy distribution, if we go back to sampling stats, neither of these things hold for Cauchy distribution with unbound variance. But back to Chebyshev, what they say is that if we have finite variance for all epsilon greater than 0, the probability that our mean squared random variable, or the tail probability of our mean squared random variable is greater than or equal to epsilon is less than the variance by epsilon squared. And so this whole thing is kind of trying to give us clean bounds that we can then work with for our weak law of large numbers. So going forward, so to prove this, so for all epsilon delta proofs, we always kind of say we first pick an epsilon and 0. And I think that doesn't work. So then let's just start with our probability. And we can square both sides. And here, what we can do is now the probability of something greater than something. Oh, well, now we know that that whole thing is bound by something by Markov inequality. So here we can actually use Markov inequality and say that this whole thing is actually less than the expectation of the first thing by the constant epsilon squared. And if we take the expectation of a mean squared random variable squared, what is that? Oh, well, that's actually the definition of variance. So that actually ends up equaling the variance of x by epsilon squared. So this is the exact same this is the exact same now as our Chebyshev inequality. So we've kind of proved our Chebyshev inequality, and now we can use that where we need. Um, and so now we can actually go back finally to our main course, our entree of this video, and that is the weak LLN. And so this is a extremely, extremely, extremely important theorem, and it's used everywhere in probability and statistics. And it states that if x1 through xn are IID and have finite variance, our sample mean converges in probability to our population mean. So now using all the tools we've gathered, we can finally take a stab at proving this. So we'll start by taking the limit as n goes to infinity, because we can do that using convergence and probability of the probability that our sample mean minus our population mean is greater than some epsilon. So now there's kind of a bigger picture problem here. This is from the sample. This is from the population. What does our Chebyshev inequality say? Can we just go one step and bound this by the variance over epsilon squared? I'm not sure, because if we go very, very closely at our Chebyshev inequality statement, this is from a random variable x, and this is the mean of that random variable x. No, we cannot just go straight into Chebyshev inequality and say that we're bounded by some variance. We kind of have to do some massaging using our sampling statistics theorem. So next, we actually want to kind of bring this into the sampling world rather than the population world. So we can actually use that first theorem that I introduced about sampling statistics, saying that for any IID set of random variables with finite variance, besides the Cauchy distribution, um, our population mean is the same as the expectation of our sample mean. So now going back, we can say that our population mean is the expectation of our sample mean. And now we have something that's in the sampling domain, we have the mean of something that's in the sampling domain, and we have a constant. So given that, it's now very easy for us to use our Chebyshev inequality. So we can now just kind of quickly say that by Chebyshev inequality, this whole thing is less than the variance of x bar n over epsilon squared. Now, what is our variance of x bar n? Well, that's also from our sampling theorem. The variance of x bar n is our population variance by our number of samples. So now this whole thing is just population variance by number of samples by or I forgot some limits. The variance of x bar n by epsilon squared by Chebyshev inequality. And then now our variance of x bar n is population variance by number of samples by epsilon squared. And if we have any constant as n goes to infinity and n is on the denominator, well, we know that obviously equals 0. So therefore, for all epsilon, as n goes to infinity, our sample mean converges in probability to our population mean. And that is the entire statement of the weak law of large numbers, which we have just proven. Thank you.